Hello, this is Bob Schmidt again. This is one of a series of videos that's designed to provide a common language and understanding of quality control. The objective of this video is to help you understand the concept of capability. So this series of videos explores three concepts that are fundamental to quality control. These are stability, capability, and controllability. In the last video we discussed stability, and you should now have a good understanding of that concept. We'll cover capability in this video and cover controllability later on. Process capability is a little easier to understand in a manufacturing context than in a laboratory context. So for that reason, I'll do this in two steps. I'll introduce it using a manufacturing context, and once the concept is clear, we'll move on and describe how it's applied in the laboratory. Process capability is the relationship between the allowable variation to the actual variation. And this index tells you how well your process can meet your customer's requirements. In the graph above, the customer has specified a target and provided a lower and upper specification limit. Notice this is different from a lab because we don't have targets. So in the manufacturing context, this is a little easier. So here, the product is acceptable as long as the outcome is within the limits. For example, you can imagine a manufacturing process that produces a reagent with a target concentration of 10 nanograms per mil. The product is acceptable as long as it's between 8 and 12 nanograms per mil. And the histogram shows that the output of the process, and you can see that it's centered between the specification limits, and the variation is relatively low compared to the width of the specification limits. This is a capable process, and it will rarely produce an unacceptable result. I like to think of process capability as wiggle room. If you have high capability, there's lots of room to maneuver without producing unacceptable results. Well, here's a couple other examples, and shows how things can go wrong. The upper panel shows a capable process, and this is the one we saw in the previous slide. The middle panel shows a process that's centered but imprecise. The width of the output is large relative to the width of the specification limits, and this process will always produce a significant volume of unacceptable product. It's not capable. It can only become capable by either changing the specification limits, widening them, or by redesigning the process to reduce variation. The lower panel shows a process that has low variation, but it's not centered. This process is not capable because it will consistently produce unacceptable product. It can become capable by either renegotiating the specifications, reducing the variation, or by centering the process. Reducing variation or centering the process could require substantial process redesign. As you can see, process capability involves comparing the voice of the process, the natural variation of the process, to the voice of the customer, which are the specifications. This comparison should be based on common cause variation. Specifications in a laboratory testing are different from a manufacturing or service process. In manufacturing, we're given an absolute target. Say, for example, we have a reagent manufacturing process for saline solutions. We could measure the concentration and determine whether each bag of saline conforms to the standard. In contrast, in laboratory testing, our product is information. And suppose we measure the sodium level of a patient, Joe Jones. We have no idea what Joe's true sodium level is, so we don't have a target to use for comparison. The only specification we have is the amount of error. And we don't care what the value of Joe's sodium is as long as we measure it correctly within a certain limit of error. This limit is called the total allowable error. And you'll get this number from your medical director. It represents the point at which error might affect patient care, leading to a change in diagnosis, prognosis, or treatment. And you can think of it like this. Suppose Joe Jones' true sodium level is 135 millimoles per liter. Our measurement will have some error. And how big would this error have to be to affect Joe's care? And this gives you an idea of what the meaning is of the total allowable error. Let's look at capability in a laboratory situation. We have the total allowable error, designated here as TEA. Results with an error greater than this are unacceptably inaccurate. We'll call these serious errors. And there's indicated by the red area there, and the area there is the serious error rate. The total allowable error comes from proficiency testing or is based on biological variation. You can imagine that if a person's sodium varies by 5 millimoles per liter on a daily basis, you don't need to measure sodium at a precision of 1 millimole per liter. You probably only need to know sodium, say, within 2 times the natural variation. The imprecision, or S, comes from the process behavior chart and is the standard deviation of the common cause variation. This is one of the reasons why stability is so important. We can't evaluate capability unless the process is stable. Bias is obtained by comparing your proficiency testing results against the standard. Any single proficiency testing event would be only an estimate of the bias. You would average the error from several proficiency testing challenges to obtain a better estimate of the bias. The serious error rate is the percentage of results with unacceptable error. Those are errors greater than the total allowable error. We usually don't know whether an individual result is unacceptable, but on a statistical basis, we can calculate the percentage that are unacceptable if we know the bias, imprecision, and the total allowable error. No test is perfect, and there's always a chance of unacceptable results. And the acceptable error rate is dependent on the medical context, and it's determined by the medical director. A risky test would require a low maximum error rate, say 1%, whereas a 5% maximum error rate might be acceptable for a less risky test. Obviously, we should strive for as low an error rate as possible, which is one of the reasons for the war on variation. It's important to recognize that any deviation from the true result is an error, but we're only counting errors greater than the total allowable error, and we'll just call those serious errors. Risk depends on the impact of a test. And for example, chemotherapy has a significant impact on a patient, and a test that determines whether a patient receives chemotherapy would have a high impact. The risk also depends on whether the test is a key determinant of a medical decision. For example, imagine a genetic test that will determine whether or not a patient receives chemotherapy. This may be the only test, and therefore the decision may rest entirely on the results of this test. In this case, we'd have very low tolerance for unacceptable results. On the other hand, consider a troponin for a heart attack. This is a high impact situation, but troponin is just one of many sources of information, such as signs and symptoms, EKG, echocardiogram, and other biomarkers, and so forth. This test is less risky because it's not the sole determinant of the diagnosis. A physician may well question an erroneous troponin result in this context. In this case, a slightly higher error rate might be acceptable. Clearly, we want to eliminate all serious errors, but that's impossible. The maximum error rate is an index that is related to the consequence of errors and is determined by the medical director. Let's look at the impact of bias on the error rate. In the upper graph, we see a relatively low bias, and a small amount of testing exceeds the allowable error rate. So the total serious error rate is low. In the bottom panel, the bias is increased, moving the distribution of results closer to the limit of total allowable error. Now the proportion of serious errors has increased, and that's shown by the red area to the right. And now let's take a look at the impact of imprecision on the serious error rate. In the upper panel, we see that imprecision is relatively low, and a small percentage of results exceed the total allowable error, so the error rate is low. In the bottom panel, the bias is unchanged, but the imprecision has increased. And you can see that the proportion of results exceeding the total allowable error has increased. And this shows that the increased variation increases the serious error rate, and this is why we are waging a war on variation. Now let's look at how capability is defined in the laboratory setting. In lab testing, we don't have a target, so we describe capability in terms of the allowable error. The interpretation is the same. That is, that capability represents the wiggle room we have for error. A capable process has lots of wiggle room. You can think of the total allowable error as an error budget. Bias consumes some of the allowable error, so we subtract that away. The remainder is the true allowable error, and we compare that to the natural variation of the process. Ideally, we'd like a ratio or sigma level to be something like 5 or 6. The process capability tells us whether a stable process. The process capability tells us about the performance of a stable process. A capable process will have a very low serious error rate. This table shows the serious error rate as a function of process capability. For example, at a signal level of 3, we'd expect 3.3% serious errors. I think you can appreciate that this is an important characteristic. If the capability or signal level is unacceptably low, we have to go back to our process. And you can see that high capability or high signal levels, say around 5 or 6, are associated with very low error rates. And ideally, we'd like all of our testing to perform at this level. Capability not only tells us our current error rate, but it also tells us the maximum shift that we can tolerate in a process. In the upper panel, we see a very capable process. There is some bias, but the variation is small, and the distance from the mean to the total allowable error boundary is much greater than the variation of the process. We'll have virtually no serious errors in this situation. Now let's suppose there's a systematic error, so that there's a shift in the mean of the process. This is shown in the bottom panel. The bias is the same, but now we have a systematic error that has moved the mean of the process by an amount delta SE, so that the mean is now closer to the boundary. How much could the process shift before we start to get worried? Well, this depends on the maximum error rate. If the maximum error rate is large, we can accept a bigger shift and allow the mean to get closer to the boundary. If the maximum error rate is small, we cannot let the mean get close to the boundary. In that case, we can only tolerate small shifts. We define the distance of the mean from the boundary by z times the standard deviation. You can think of the quantity z times s as a buffer zone that protects against serious error. Z depends on the maximum allowable error rate, and we determine z from probability tables. For example, if the maximum serious error rate is 2.5%, z would be 1.96, and if the maximum error rate were 5%, z would be 1.65. As we showed in the last slide, the maximum error rate determines how close the mean of the distribution can get to the total allowable error boundary. And this distance determines z, which is expressed in multiples of the standard deviation. And as we showed before, we can think of z as a buffer zone required to ensure that the amount of serious errors are less than the maximum error rate. We can use the analogy of an error budget. The total error is consumed by bias, the buffer zone, and the critical shift size, as shown in the upper equation. Rearranging, the maximum shift is given by the second equation. You might recognize the term in parentheses as the process capability. The maximum shift is an important number to know. It tells us the magnitude of systematic errors or shifts that we need to be able to detect in our control scheme. Shifts smaller than the critical shift size will not cause the serious error rate to exceed the maximum allowable error rate. We need to know when the process has changed in a way that would cause us to exceed the maximum error rate. Thus, we need our control scheme to produce a signal when a shift of this size occurs. Let's consider the relationship between variation and the critical shift size. In the upper panel, we have low variation, and we see that the mean of the distribution can be quite close to the boundary without exceeding the maximum error rate. And notice when we're talking about the error rate, we're talking about the area to the right, which is different from the total allowable error, which is not a rate, it's an actual magnitude of error. In the lower panel, the variation is much larger and the mean must be further from the boundary to keep the serious error rate below the maximum. The point is the critical shift size decreases with variation. So you're probably thinking, so what? Well, this is actually important because it's easier to detect larger shifts. More variation means that we need to detect smaller shifts. And to do this, we need a more powerful detection scheme. And such schemes are expensive. In addition, they are often not as powerful as we'd like, which increases the risk to patients. Thus, once again, we find that variation is the enemy because it increases cost and increases risk to patients. Higher capability means better control. Let's step back again and take a bird's eye view. We've now covered two of the modules in this graph, so it should be starting to make more sense. As we saw in the last video, process variation is used to assess process capability. You now know why that's important. Capability is a key performance index that is used to assess risk to patients. Capability analysis also tells us the size of errors we need to be able to detect. We can only evaluate capability when the process is stable. The variability is also used to determine the size of errors that we can detect when the process goes out of control. And this is called power analysis. And the power analysis depends on the QC plan and the size of variation. Controllability is about reducing the risk of reporting unacceptable results when the process is out of control. That is the risk of making serious errors. Say the process does go out of control. Our ability to detect it depends on the size of the error we can detect. This comes from the power curve, which will be described in an upcoming video. The power curve depends on the QC plan and on the process variation. The process capability tells us the size of errors we need to detect to prevent reporting unacceptable results. Obviously, big errors are easier to detect than small errors, and a capable process only requires you to detect big errors. Designing a QC program is about selecting a plan that can detect the errors you need to detect at reasonable cost. Note that control is easy when the process is capable, and a process is capable when the variation is low. We can select a less costly QC plan when the process is capable. Therefore, we want variation to be low. And this brings us to the last piece on the diagram, which is process improvement. We want to make changes to the process to reduce variation. And when we do this, we start all over again and examine whether we can choose a less costly QC plan and reduce risk to patients. We'll talk about all this in detail in future videos, but for now, this is just a preview of where we're going, and you should be understanding more and more of this overall system. The previous diagram showed a systems view or a bird's eye view of the overall quality control process. You've seen this slide before, and you're probably about ready to call the dead horse protection society. But this is important, and I want to emphasize this. The whole system depends on three concepts: stability, capability, and controllability. Let's summarize what we've covered in this video. We covered four important topics. First, we covered capability. And this tells us the performance of the process when it's stable. This is something we want to know. We also looked at the impact of bias and imprecision on capability, and we see that variability hurts capability. And we also touched on the maximum error rate and how that depends on the medical context. And finally, we covered the idea of a critical shift. This is a key input for designing a control plan because our control plan needs to be able to detect a shift of this size if we are to remain within the maximum error rate. I think you'll probably agree that all of these things are important and worth knowing. Okay, that's it for this video, and I hope you found it useful. Please contact me if you have any questions or would like to talk about anything I presented. And thanks for listening.